Hello and welcome to College World. Here we are at our final chapter for our C4 tutorials, and now we will be totally done with C4. For you, of course, this would not be the end as you would have more practice sessions and such, so await more tutorials and more practice to ensure that you ace your tasks. For now, I'm going to give you a brief introduction about our 6th chapter, which is technically one of the most important chapters because students find it most challenging, and this is the integration chapter. So, first of all, in order to be able to solve integration, you don't need to memorize rules only as much as you need to understand what you're actually doing. This is why I'm going to give you a brief introduction about integration. So, what is integration? You can think of integration in three ways. The first thing you can think of is, which is the rules way, is that what you do is that you add 1 to the power and you divide by the new power. So if we're integrating x to the power and the x, this will be our answer. This is the general rule. But then if we want to understand what we're doing, we can actually understand it. We need to know that integration is also known as the antiderivative. In other words, it is what we did in differentiation, but the exact opposite. So what we did in differentiation is that if we had 3x squared, what we did is that we multiplied the coefficient by the power and then we reduced the power by 1. Now, if we do what we did here, using the rule to this, what we're going to do here is we're going to add 1 to the power, so x squared, and we're going to divide by the new power, which is actually going to lead us back to the number we had. So this is differentiation and this is integration. This is why integration is the antiderivative of the differential here we got. If we integrate something, we go back. And if we want to understand this even further, we can actually use the graphs. We can actually use the graphs. When we were thinking of graphs, here, let's say we had velocity versus time. This is velocity and this is time, and we had a certain curve here. Now what we said is that if we take the slope at any given point, so let's use a different color here, we said that the slope is actually the differentiation, and we said that that means dv by dt, and the rate of change of velocity with respect to time gave us acceleration. Now, if I instead wanted to go back, so if I instead wanted to go back, instead of dividing velocity, if we actually draw our triangle here, this was here v, t, and acceleration. Acceleration is change of velocity over time. Now, if I want to go back from acceleration, I want to go back from acceleration here, what I'm going to do is I will have my acceleration time graph, and I want to go, let me go back, not that back, yes, here. So if this was time and this is acceleration and I wanted to go back to velocity, what I'm going to do is that I'm going to multiply, if I had acceleration and I wanted to go back to velocity, what I'm going to do is that I'll multiply acceleration with time. In other words, if this is our curve here, it is increasing, the slope is decreasing actually, so from 0, okay, anyway, whatever it will look like, it doesn't have to be the same. I'm not going to do the math now, but you're going to actually multiply the acceleration by the time. What you're going to get is the area. Here, if you do this for the actual graph and you get the area under the velocity time graph, it is like you're multiplying velocity by time, which is going to actually give you the distance or the displacement s. And this is how you understand integration. Integration is the reverse of differentiation. When you differentiate something, you find the change of a change per unit time. So you're dividing the y-axis by the x-axis. With integration, you're doing the opposite. You're multiplying the y-axis with the x-axis, and you're finding the area. In other words, differentiation gives you the slope, while integration gives you the area. Now, if you even go a step further, and then as we did here, if we have an if we actually have an area, so let me scroll down a bit, and here. So if I actually had an area, and let's say this was, ignore the creepy graph, but let's say we had this area right here, and we wanted to integrate it. So we're actually integrating a whole 2D area instead of a line. In that case, you're multiplying something 2D by another something. So if we said this is like a surface area, an area, and you're multiplying it again. So if this was in meters squared, you're actually multiplying it by another meter, and you're getting the volume. The point of this is to tell you is that when you differentiate something, you get its slope. When you integrate that same something, you get the area under its graph. If you integrate an area, you're going to get the volume. All these will be used in multiple problems and cases we're going to face in this chapter. This was only a brief introduction to how you think of integration, but we're actually going to face multiple types of integration. We're going to integrate exponential functions. We're going to go through trigonometric identities and their use in integration. We're going to get to know something called integration using substitution. We're going to do it by parts. We're going to move on to finding the area and volume like we did in the introduction, just as but actually in depth. We're going to use our very first chapter, partial fractions and integration. We're going to know something. We're going to know something called the trapezium rule, which is also used in order to find the area or the volume. So actually the area, the trapezium rule, and we're going to even solve differentials using integration. All these we're going to come to face in different cases throughout this tutorial for integration. So stay tuned.